Percept-WAM, Perception-Enhanced World Awareness Action Model for Robust End-to-End Autonomous Driving.
And this paper, it really gets to the heart of a core fragility in these big multimodal driving systems. For all their promise, these vision language action models, or VLAs,
Right.
they just fall apart when it comes to precise spatial grounding. They can reason, sure, but they can't accurately localize things, especially in those, nasty long-tail scenarios. A small object in the rain, a pedestrian far away.
And that's the real bottleneck, isn't it? If your whole system is built on something indirect, like a Q&A style of reasoning, your decisions are always going to be built on a wobbly foundation.
Exactly. And that's what's so clever about Percept-WAM. It sort of weaves the explicit 2D and 3D understanding directly into the VLM itself.
It forces the model to get the geometry right first.
Yes. And they do it with these structured tokens they call world tokens. You have World-BEV for the camera's perspective view and World-BE for that top-down bird's eye view. And these aren't just, abstract features. They explicitly encode metric coordinates, confidence scores. It's a real localizable map of the world.
The results are they're stunning because it shows this isn't just some generalist model, it's a specialist. It's matching or even beating dedicated detectors. We're talking 51.7 MAP on COCO and a crazy 58.9 MAP on nuScenes BEV 3D detection.
And when you plug that into the action pipeline, you see that end-to-end improvement. It hit 90.2 PMDS on the NaviSim benchmark, which, that's significantly better than competitors like Diffusion Drive. And what's critical is that it does this efficiently. The latency is down to 707 milliseconds. This isn't just a research idea. It's engineered to be practical.
Okay, let's really unpack that. Why were the old VLA paradigms failing so badly in the first place?
Well, it almost always comes back to geometry. In autonomous driving, the moment things get complex, heavy rain, a tricky night, turn-tiny geometric errors just get amplified.
A small bias in detection.
Right, or a few degrees of error on a bounding box, a mistake in the BEV map. Any one of those can cascade into a catastrophic planning failure.
And the big vision language models, they just weren't designed for that kind of geometric precision. They were built for semantic understanding.
Exactly. The whole QA-style supervision, which you see in frameworks like Emma, it basically treats spatial understanding like a language problem. You ask it, where's the car? And it gives you a text answer. The problem is that's a really indirect signal for localization.
So the model might say it sees a car, but the actual coordinates, the velocity, the orientation, all the stuff you need for microplanning is either missing or just shaky.
That's the critical danger, absolutely. If your planner is getting these low-confidence, flickering detections frame after frame, the whole system becomes unstable. It just lacks that persistent metric grounding you need for safety.
Okay, so what about the other popular approach, the diffusion decoder pipelines?
Well, they're fantastic, for one thing. Generating beautiful, smooth trajectories. They make the car move very nicely, but they often skip the hard part. They don't explicitly learn the perception task first. They're kind of working off these high-dimensional, latent codes of the environment, not a structured world state.
So they might generate a safe path because they've seen something similar before, but they can't really reason about a totally new, complex situation that needs both semantic and spatial understanding.
Precisely. And that's the gap Percept-WAM was designed to bridge. It embeds that explicit, persistent world state, the 2D and 3D evidence, before any high-level reasoning happens. You force the model to reason over hard, spatially grounded evidence. That's the big shift.
That structural guarantee feels really powerful. Let's get into the nuts and bolts then, these world tokens. How do they actually unify 2D and 3D perception?
The unifying idea is the output format. Both the perspective view tokens and the bird's eye view tokens encode metric coordinates right alongside a calibrated confidence score. So you get this reusable base of evidence for everything: downstream, detection, segmentation, planning.
Okay, so let's start with the image plane. The World-BEV, or perspective view tokens. Why are they so important?
You can think of them as the frontline workhorses. They're responsible for detecting everything across all distances, especially the hard stuff, small objects, things far away, things you might miss in bad weather. It all starts with the raw images going into the VLM backbone.
And instead of just getting a soup of features, they structure the output into this grid of World-BEV tokens.
Yep. Conceptually, they kind of patchify the feature space, say, into a 10 by 10 grid, and each little cell in that grid acts as a localized query. It's responsible for predicting objects just within its own little area.
And the output itself is formatted almost like
Yeah,
Like
yep.
text, right? It's autoregressive.
Yeah, it's correct. It uses the VLM's native ability to generate structured text. But instead of words, it's spitting out things like class, then box coordinates, then confidence. It's a really elegant way to unify these different outputs under one framework. For 3D, it just adds the 3D coordinates, size, yaw, and so on.
But spotting distant objects requires incredibly high-resolution images. How do they handle that without the memory just exploding?
This is where they use a trick from intern-VL dynamic tiling. With high-res images, the cost of attention can grow quadratically. It's a killer. So dynamic tiling breaks the image into partitions, processes them, but then it fuses the features back together using global positional alignment.
So you get to keep the long-range detail without the computational nightmare.
Exactly. You can still see that traffic light way down the road.
Okay, so World-BEV gives us that rich detail from the camera, but now we have to get into the 3D world, the bird's eye view, which is really the cornerstone for any kind of planning.
Right, and the World-BEV tokens are what create that top-down space. They typically use a 40 by 40 grid of learnable query tokens. Now, these tokens don't look at the image directly.
They query the PV tokens.
They query the World-BEV tokens using cross-attention. And that's the magic step. That's the mechanism that lifts all that 2D visual evidence up into a 3D BEV representation.
That cross-attention step is where the perspective gets transformed into real-world metric coordinates on the ground plane.
Exactly. And what's really smart is that this is all designed to work with just cameras. In that case, the BEV tokens are just randomly initialized. But it's also multimodal ready. If you happen to have LiDAR, you can use features from a classic encoder like point pillars to initialize those BEV tokens.
So it's not just using the LiDAR data, it's using the geometric consistency from the LiDAR to give the camera-based system a better starting point, a better initial guess for the 3D structure.
It gives it a massive head start, boosts geometric consistency like crazy,
Right.
and from there it can do all the BEV tasks, 3D detection, map segmentation for things like drivable areas or crosswalks. It's all handled within that same unified token framework.
Okay, so the architecture enforces better perception. But there's this classic VLM problem you run into. They're systematically overconfident. You can have a perfect geometric output, but if the confidence score is wrong, it's just noise. Which brings us to this IoU-based confidence prediction.
This is such a crucial fix. General LLMs, they just suffer from this. You'll see it give a class score of, say, 98%. It's sure it's a car, but the bounding box is garbage. It's way off.
It's confident about what it is, but not where it is.
Yes. And that generates so many false positives that the downstream planner has to somehow filter out.
So how does this IoU-based confidence solve that?
It's actually quite simple. They just add an extra token to the output sequence for every single box. A predicted intersection over union score. It forces the model to bet not just on the class, but on the quality of its own localization.
So instead of just saying, I'm 98% sure that's a car, it has to say, I'm 98% sure it's a car, and I'm 90% confident my box is accurate. The final score is the product of both.
Which is just inherently more robust. But training this was tricky. The ablation studies show that just using, ground truth data didn't really work.
They needed a data set that reflected the model's actual errors.
That's it. They did something really clever. They generated a data set using predictions from an intermediate stage of the model's own training. So they were training the confidence predictor on the real failure modes and imperfections of the model itself.
That's like self-aware calibration.
It is, and it gave them huge precision gains. We're talking a 1.5 to 2.3 AP gain just from filtering out those confident but badly localized boxes.
That's just brilliant. Okay, let's talk speed. We have the super complex multitask VLM doing all this work. 707 milliseconds of latency is. That's a serious engineering accomplishment. How did they pull that off?
It really comes down to two main things: parallelism and stability.
Yeah.
First, all the dense object predictions across those PV and BEV grids are decoded in parallel, which really helps with throughput.
But the real demon in autonomy is always sequential processing, right? Maintaining state over time.
Always. And for that, you need a streaming KV cache for these long visual sequences. So for trajectory prediction, the tokens at any given time t only attend to the features from the two most recent frames, T and T1.
But using a cache like that, where you're constantly dropping old frames, it's a recipe for instability and distribution drift. You get all sorts of weird issues with positional embeddings.
It's the classic speed versus stability trade-off. Yeah. But they have this really novel dual recomputation strategy to deal with it. It involves small local refinements, the most recent cache entries, and then periodically a bigger global recomputation of the cache.
So it's like making constant small corrections, and then every so often you hit a reset button to realign everything globally and stop the drift.
That's a great way to put it. And that dual approach is what cut the inference latency by 40%. It's what makes that 707 millisecond number possible without a big hit to accuracy.
That really does put this in the realm of real-time application. So let's connect all this amazing perception to the final stage, the actual driving action, the world action tokens.
Right. So for reliable planning, you need to pull features from all three perspectives. You need the BEV for context, the PV for all the rich semantic details like signs, and of course the ego state for your own car's kinematics. The action tokens have to fuse all of that.
And they use a query-based decoding approach with 4 parallel sets of queries to do that. Can you walk us through those?
Sure. You have 3 queries that are modality specific. One for PV, one for BEV, and one for ego state. And through attention masking, they can only interact with their own feature space.
So that ensures you get a strong representation from each modality before you try to fuse them.
Exactly. And then you have the final query, Qful, which has access to everything. And that's the one that decodes the final trajectory sequence. It prevents any one modality from getting drowned out.
And the quantitative results show that this whole integrated pipeline works.
Oh, yeah. I mean, look back at the perception scores. Getting 0.589 MAP on nuScenes BEV 3D detection, that's profound. For listeners, you have to understand that's better than dedicated classic detectors like point pillars that are often heavily reliant on 3D LiDAR data.
So a VLM end-to-end is getting better 3D results than models specifically optimized for 3D inputs, all because of that robust backbone and the structured projection.
It completely validates the approach of putting explicit geometric conditioning inside the VLM. But the real test, of course, is the planning benchmark on NaviSim. And that's where their 2-stage training strategy was so important.
The Percept-WAM model.
Right. They trained the perception really heavily first, and then fine-tuned the planner on top of that super strong base. And that's what delivered the 90.2 PMDS score, beating diffusion drive.
But it seems like even with perfect perception, the planning method itself was just as critical to get that score in a closed-loop simulation.
Absolutely. They found that just, simple autoregressive generation wasn't stable enough for closed-loop success. Even with perfect perception, the model might generate a path that's just a little bit unstable, and in a closed-loop system, that error compounds and you fail.
What did they do?
To get that top score, they used a technique inspired by Hydra MDP. Instead of just generating one path, they generate a small vocabulary of possible good maneuvers, and then the model scores them against the world state to pick the absolute best one.
So it's more of a generation and selection approach, which adds a layer of stability.
Exactly. And that stability is what translates into robustness in the real world. Qualitatively, this is where the model just shines. In the paper, they show it handling these really hard scenarios where other models would just fall apart, yielding to a cyclist who's partially obstructed during a night turn, avoiding a jaywalker in the rain.
That open vocabulary generalization, handling new combinations of things, that's the ultimate proof that the strong perception layer is actually translating into better decisions.
Percept-WAM has, I think, fundamentally challenged the status quo here. It successfully unifies specialist-level perception inside a single VLA model, and then it translates that geometric competence directly into high-performance, low-latency planning. It really does close the loop between seeing and acting.
It addresses that core geometric inadequacy that these general VLMs have always had, especially in a domain this safety critical. But the final piece of the puzzle, it seems, always comes back to the policy itself.
And that's the next frontier the paper points to. Once you've solved perception, you have to enforce system-wide consistency. Their future work is focused on a unified reinforcement learning framework, specifically offline or online RL, using rollout-based rewards.
That's a really fascinating pivot. Is that shift telling us that these systems now have to learn to see the world not just accurately, but through the lens of maximizing future rewards?
I think that's exactly it. The goal is to explicitly couple perception accuracy with the quality of the trajectory. It's not enough for the VLM to just say, I detected that car perfectly. The system has to learn to prioritize the perception details that actually matter for its survival and success over the next 5 seconds. And that, I think, is where truly consistent autonomy is going to come from.